Did you know that modeling a porphyry copper deposit is like reading the geological processes of millions of years with an impact of millions of dollars? This is not only geology, but also data, geostatistics, uncertainty, and decision-making. So, how do we go from dispersed data to a reliable resource model? In this season of the GeoEstima Podcast, we will explore the most essential deposits in modern mining. Today, porphyry copper. Join us to keep discussing and learning more about the geo-mining-metallurgical business in Chile and around the world. Starting with the basics, a porphyry copper deposit, as its name suggests, is a deposit with significant concentrations of copper. The term porphyry refers to the intrusive texture related to mineralization. These deposits are the primary copper source, contributing more than half of the copper extracted worldwide. They are also a relevant source of molybdenum, rhenium, and gold. Let's see some of their principal characteristics. The first one, porphyry copper deposits are Q-Mo deposits found in magmatic arcs associated with convergent tectonic margins, where the mineralization relates to small intrusive apophyses and associated breccias that are emplaced at shallow depths, ranging from 1 to 6 km. For example, in Chile, many productive magmatic arcs or metallogenic belts are recognized. The Middle Miocene, Lower Pliocene, Bilayameus said, Middle Miocene, Upper Eocene, Lower Oligocene, Paleocene, Lower Eocene, Lower Cretaceous belt. The second one, the mineralization of Cu and other elements, is related to successive hydrothermal events that start during the last cooling stage of the intrusion and progressively alter and mineralize both the intrusion itself and the host rocks. The third type, Cu mineralization, occurs in a disseminated manner or the stockwork of quartz veins, generally classified as A, B, and D veins, or in the matrix cement of hydrothermal breccias. The fourth one, primary mineralization and alteration, occurs disseminated or in ATP quartz veins, and is generally concentrically zoned around the intrusives, with a central zone where chalcopyrite prevails, with lesser bornite and sometimes digenite, which grades outward to chalcopyrite, pyrite, pyrite, chalcopyrite, and pyrite associations at the periphery. The hydrothermal alterations consist of potassic alteration, potassic or biotitic, in the central zone, grading to chloritic zones or propylitic alteration, chlorite, epidote, calcite, and pyrite. In the periphery, molybdenum is associated with intermediate hydrothermal stages, generally expressed by B-type quartz vein mineralization, with molybdenite, chalcopyrite, and pyrite. The fifth one, as the hydrothermal system incorporates more meteoric water, a later stage of phyllic alteration with quartz, cerussite, minor chlorite, and pyrite is superimposed on the early alteration and mineralization. Cerussite generally represents illite and muscovite assemblages that replace or alter feldspars and mafic minerals. The associated mineralization occurs as DTP quartz veins, which contain pyrite with lesser amounts of chalcopyrite and bornite. The sixth one, if the system is tectonically dynamic, high sulfidation hydrothermal events with Cu and As mineralization, sulfur salts, or epithermal events can be superimposed. These superimposed events are expressed as veins or breccias with enargite, bornite, or tetrahedrite, tennantite, and kaolinite, dicite, or pyrothelite alteration. The seventh one is that porphyries can form within complex structural configurations that act during pre-mineralization, syngenetic, and post-mineralization stages. These structures can control the distribution of Cu and Mo mineralization, as well as superimposed mineralization systems. There are several examples of large porphyry systems affected by post-mineral faulting, such as Chucucumata or Rosario, Coloasi district. The eighth point is that there are porphyries that, after their formation, are affected by supergene processes which significantly modify the configuration and distribution of the original mineralization through deposit weathering due to tectonic uplift and erosion. In this case, The action of surface meteoric water causes oxidation and leaching of primary sulfides, which mobilize, transport, and redeposit the original Cu mineralization, generating a characteristic mineralization profile with a leached and barren zone at the top, followed by oxide zones and / secondary sulfide zones below. As a result of these supergene events, it is also possible to have exotic Cu mineralization through the remobilization of mineralization outside the zone where the porphyry was originally emplaced. Finally, besides copper, porphyry copper deposits can contain associated minerals such as gold and molybdenum. For this reason, they can be subdivided into copper molybdenum, copper gold, and copper gold molybdenum porphyries. In general, they are large tonnage and low-grade deposits. The ore bodies typically contain between 50 million and 7 billion tons, with average Cu grades ranging from 0.15% to 1.5%, and Mo grades ranging from 0.01% to 0.04%. In my experience, I can say that no two porphyries are the same. There are deposits with minimal structural influence in their formation, and others that have very complex structural configurations. Most porphyries are hosted in volcanic or intrusive rocks, although there are a few cases in which they are hosted in sedimentary rocks. There are porphyries with extensive mineralization development in breccias, and others where the mineralization is predominantly hosted in the host rock. Some systems are well preserved from erosion, and others have suffered high erosion rates. Therefore, what remains today are the remnants and deeper parts of the original system. Finally, there are porphyries where the economic mineralization is primarily primary, as in the case of Rosario and Collahuasi, and others that relate to supergene events, Escondida, El Salvador, Ugina. Therefore, geological characterization work and geological conceptualization are fundamental to understanding these deposits and to generating geological, grade, geometallurgical, geotechnical models, and others. Conceptual model, don't read. That's why, when modeling the geology of a porphyry copper deposit, it's essential to build a conceptual model that characterizes the different elements that make it up. This is where we need to incorporate an understanding of the geological features of each event, and chronology becomes a key factor when interpreting the geological model of the deposit. Exploitation, don't read. Let's move on to exploitation. Most porphyry copper deposits are exploited by massive methods, such as open pit mining, due to the large horizontal extent of the deposit, or underground methods, including block caving or panel caving. The metallurgical process depends on the type of mineralization. Generally, for primary and secondary sulfides, flotation and concentration are carried out in concentrator plants, with copper concentrates being the main final product. However, some operations perform smelting of the concentrates, producing blister copper, and then Q cathodes by electro-refining. Ore processing in concentrator plants requires tailings management and process water management. When the mineralization is oxidized, or consists of secondary sulfides, acid leaching process in heaps or vats, solvent extraction and electro-winning processes are applied, which ultimately lead to the production of copper cathodes. Given the size of these deposits, it is common to have leaching and concentration processes in the same operation. Most famous deposits, don't read. Before concluding, we want to mention some of the most essential porphyry copper deposits around the world in terms of contained mineral resources and industrial production. As you can imagine, most are located in Chile, where we can mention the iconic Chuquicamata, a large-scale deposit that has been in operation for more than 110 years and belongs to Codelco. Today, Mina Escondida is the world's largest producing porphyry copper deposit, operated by BHP. Another important mine is Collahuasi in northern Chile, currently the world's third largest copper-producing mine. Other examples are the Los Bronces Adina complex, operated by Anglo-American and Codelco, respectively. Also, Los Palambres, operated by Antofagasta Minerals, and El Teniente, operated by Codelco. In other parts of the world, the Grasberg mine is located in Indonesia. This is a Kuo porphyry with associated skarn mineralization operated by PT Freeport Indonesia, a subsidiary of Freeport Macmore, with significant participation from the Indonesian government. The mining operations include both open pit and underground methods. Another case is Bingham Canyon in the United States, operated by Kennecott Utah Copper Corporation, a subsidiary of Rio Tinto. Turquoise Hill Resources, a subsidiary of Rio Tinto, operates the Oyu Tolgoi mine in Mongolia. Other significant deposits are located in Peru, such as Toquepala and Cerro Verde. With this, we conclude our episode of porphyry copper deposits. In the next episode, we will discuss another type of mineral deposit, the IOCGs. We invite you to stay tuned for our next episode, where we will continue discussing and learning more about the geomining and metallurgical business in Chile and around the world.